Okay, so good morning, everyone. How are all of you today? Great.
Great, I'm doing great. We're coming into the last couple of weeks of the semester. We literally only have 2 weeks left, right? And then we have a final exam. Yeah. The assignment sheet should be going around, and it is, right? That's right. So today we are going to continue our conversation from last class. Just to keep that in mind. What did we talk about last class? What did we talk about last class? What was that, Anissa?
Something to do with risks. Could you give me? Could you elaborate a little bit on that? Risk averse. Risk averse.
Yeah.
We had risk.
We used
We had risk averse. Risk neutral, and those risk loving folks. And I went through like examples of gambling or casinos. They sort of rely on people being risk loving. Insurance relies on people being risk averse. Most people tend to be pretty risk averse. We can get into the behavioral economics of it and prospect theory, but in general, we can have these various distinctions. Refers A, EX, indifferent between A and EX, refers EX to A. What's the relationship between EX and A? Well, what is EX? I should start there. What is EX?
I feel like I should call on someone. Let's call on someone. John? Not sure if else you can call on None? Unbelievable. I'm going to drop the class. Drop the class. Is yes. So what is EX? X, Y, Z, Y. Excellent. And what is in this scenario? What is EX set to? So what is EX? What's the relationship between EX and A? What's that saying again?
Yeah, so exactly. A is the certain payoff. EX is the expected value. What's the relationship between the two? Like, what is EX? What is A with respect to EX? Which one's bigger? Are they the same size? They're equal. Absolutely. So we're going to let EX equal A. A risk neutral person would be indifferent, but a risk averse person is really concerned about the uncertainty here. They prefer the certain payoff. A risk loving person really just enjoys the uncertainty here. It's fun. And they would go with the uncertain payoff.
How is expected value calculated? Why? How am I doing? No. Who will be asked? Sorry. Who will be asked? Yes.
Oh, V, yeah. PV with a probability times the value if it happens. And yeah, exactly equal to expected value. So this is a very helpful thing to think about.
We get our minds around. It comes up in a lot of different places. I gave you an application of it with prediction markets last time.
And we talked about prediction markets, right? Yes, great.
And so we're going to continue on with another application too.
And that is negligence. What do I mean by negligence? What is negligence? What is negligence?
It's like not caring on a sloppy way. Mm-hmm. Yeah. What's it usually put a reference to? Making mistakes.
Crime, making mistakes. Insurance. Getting closer. Now what I'm thinking of, maybe it is used a lot in insurance. What was that say? Child care. Oh yeah, negligent child care. It also has a legal reference too. What's the legal reference? Someone know? Let's imagine that you bought a car and the car was not hooked up properly and they forgot to install the brakes. And you drive the car and you crash it because it doesn't have any brakes and you really hurt yourself. So what do you're just like, well, that's life. Is that what you do?
You sued the car company because
they were negligent, right? They didn't take care, right? So it's often like terrible things happen all the time involving people's products. Sometimes the products are not assembled correctly. Sometimes there wasn't enough thought in constructing the system for it. Sometimes, for example, and this is not just true too of people buying products or consumers buying products, also applies to workers as well. And maybe there's accidents on the job. So if someone hurts themselves on the job, or if a customer is somehow harmed by a product that they bought, should the company always be held negligible? Should they always be held responsible? What do you mean? Mm-hmm. Yeah, no, that's a great example. It's a great example. So what Rebecca is referring to, this idea that we're recognizing sometimes, actually there's a law page in there that I want to unpack it. Sometimes when something bad happens, maybe you just can't prevent it. And other times too, when something bad happens, maybe it was your fault for not preventing it, right? There's a certain level of expectations. Now, what if I were to tell you though that, sometimes people forget to wear glasses, they're in a rush, and I should still sue the company because they should have hired people to stand by with a pair of their glasses and make sure that people use them whenever they're using some sort of equipment.
Well, we have to sign a non-disclosure saying that if something happens to us on the site, and it's off,
Okay, but another solution is that rather than signing that, the company who made the glasses could just stand around and hand people glasses and make sure that you wear them. Well, because sometimes people are in a rush and they forget. and like we're talking about their eyes, and it's really important. Does that sound like a reasonable thing? Why not? Why would that not be a reasonable thing?
That's self-expectation that you're talking about.
Hmm?
Is there expectation that you're talking about?
What do you mean?
That we should learn, or that person to be told, you know, especially something you should be prepared, you know, it's awesome.
Okay. Well, what if I wear the glasses and there's something wrong with the glasses because there's a little hole in them? Why is it not on me for not checking it for little holes? Anyone? Yeah?
Well, the company provides the glasses to you, saying, you know, these are good glasses and they pass our expectations that we're supposed to protect you. So you have to, like what you were just saying, what she was saying is that, you know, you have a self-expectation, but you also have there's an expectation on both sides that the company is going to give you correct glasses, but also that the person is supposed to wear the glasses and actually don't wear the glasses.
So then how do we determine when something is someone's self-expectation, when something is the company's fault? How do we draw that line?
I guess you could test the product first. Yeah, first you test the product and then you let the customer wear it.
Yeah, but you know, sometimes there's always flaws that come into it, right? So what essentially I'm getting at is that with any product that comes out, right, while you might test it, there still might be problems with it. Just in all probability, right? There's sometimes errors in manufacturing, or someone made a mistake or something like that. There's also harm that occurs when someone is hurt due to a poor product or due to poor management or something like that. You know, if you're a worker, for example. And there's also a cost to preventing the bad thing from happening. So in the case of having someone from the glasses company stand by and hand out glasses to people to make sure they work, that's like a crazy expensive thing to do. To hire people to do that would be unreasonable to ask companies to do that. At the same time, making sure that people inspect it, every little thing that they come on, make sure it's fine, that's also pretty unreasonable too. Especially if it's small, right? It might be really hard to find that error in the glasses. Right? And you might miss something that you're not even trained to find either. Not to mention, like, it would just be so time consuming to do, and time is money, as I'm sure. I don't think they let you be lazy on a construction site, right? Time is money. Gotta get this thing built. Things take forever to be built anyway. I know it's complicated. I'm not judging you, but these factors sort of boil into what we call the learned hand rule. And it's a really cool application of expected value. So first of all, as we've recognized, we shouldn't always hold people responsible just because something bad happened. There are, just to illustrate, two kinds of accidents, we could say. Maybe common accidents and rare accidents. Let me make a little table here. And if the accident happens, the accident can be big. Harm is big. The accident, if it happens, it can be small. Harm is small. Now, obviously, it's going to be a sliding scale for each of these. All right. This is really a story of probability. Probability can be, you know, 0.9 or 0.8 or 0.7 or 0.6. Just says this can be $1,000 in this can be $1,000 in harm, or $100,000 in harm, or $1 million in harm. Right? There's a lot of spectrum here. This is just to help us sort of get into what we're going to do. And this is going to be a table of expected costs. Well, we have a very high expected cost right there in the upper left-hand quadrant. Something is a really common accident, and if it happens, it's a really big deal. So, for example, if there was a construction site, you're working in a really high area,
people could fall pretty easily. So you have a safety harnesses, right? So it would be very common if you didn't have that safety harness. It would be very common, I think, if people fell. It's terrifying. It's slippery in the weather. And if you do fall, it would be a very big deal because you would be seriously injured or die. So that would be this quadrant here. Over here is a rare accident. That's not a very big deal that would happen. What would be something that is a very unusual thing that you wouldn't care about if it did happen? How often on a construction site do people drop things on their toes? All the time. So what do you wear to prevent that from happening? How likely is it that someone forgets their steel toe boots one day?
They're not even allowed.
Oh, what was that good of someone missing the fact that someone forgot their steel toe boots? It's like, you don't want to say zero, right? But it's really unlikely. So here's a case where, granted, like people drop things on the feet all the time, but in addition, that person forgot the steel toe boots, and other people didn't notice that they forgot them. So this is a really, really rare thing. And if you drop something on your foot, I'm not saying it's like something that weighs 10 tons. I'm saying it's something that weighs like 50 pounds. That hurts. Are you going to die? No. So in that particular case, this would be like a very not big deal. And it sounds like what you're talking about is, because I had to add in a whole bunch of things. I didn't really know how often people drop stuff on their foot. But apparently that happens a lot. That was pretty rare, but it happens a lot. But is it a big deal when people get dropped on the foot? Even if they didn't have the steel toe boots, is it a big deal? No, right? It just hurts a lot. Similarly, there are very rare accidents that the harm is big. And certainly in construction and really in lots of places, that's very common. Right? If we're talking like a roller coaster and someone literally gets injured on a roller coaster, sometimes that happens where they didn't like build the beam low enough and it's back there and they die right? Like that would be such an example. It's not as bad as a common accident that's really high, but it's kind of in the same category. And this is what expected value teaches us, is that even though this is definitely a problem and is a really big concern, and this is something that should be deprioritized, these two seemingly very different things are treated kind of exactly the same. It is the probability of the event happening and the result of that event. So if we're going to think about negligence, we should really consider the harm of the event in the same kind of context as we consider the probability that the event happens. We also should think in terms of how easy it is to prevent the bad thing from happening. So how expensive are steel toe boots? Give me a ballpark.
From like $1,000 to $200.
Okay. So it's like, it's really painful to drop something on your foot. You could really damage your foot if you drop it. And like you said, it's common. So while it's not like a super huge deal, it's still small, but maybe we're right here. To spend $200 to prevent this seems like a pretty good deal. Right? To prevent something that happens all the time. If a steel toe boots, though, costs $200,000, right, probably not worth it, right, even though nothing else has changed. I mean, I would also say that if you weren't wearing steel toe boots, you probably would drop fewer things. You'd be really damn careful. The other thing in economics is called the Peltzman effect. When you make things safer, people take more risks. And so there's one economist who took that. He was pretty eccentric and strange. His name is Gordon Pollock. And he took that in the other direction. He's like, okay, so if we make things safer, people take more risks. So let's make things more dangerous and people will be safer. So he coined it, we call it the Tulloch airbag.
which is when you're driving, you don't have an airbag. You instead have a wooden spike jutting out of the steering wheel aimed at your heart. Okay. You gotta be damn careful there. Be damn careful. He was kind of a mean guy, but in a folksy way, so it works for him. Okay, so let's do the learned hand rule. This rule, by the way, was coined by a judge named Learned Hand, which immediately you can tell this was not a modern rule, because who in their right mind would name their kid Learned? But some people did. And this was actually a ruling from 1947 concerning a case of United States v. Carroll Towing. Back in 1944, there was this barge located on the river. It was a part of the Hudson River, tied to a pier. And Carroll Towing was moving another barge. You know this case?
Yeah, in criminal law, you learn about this case.
It's a classic case.
Yeah.
What do you remember about it?
Just like the insurance company, they felt like they tried to argue that the boy was trespassing.
Did you... Wait, there's a boy trespassing?
Or is this the one about jumping off a plane?
Oh, no. That's, you're thinking of a different case.
Okay.
There's a lot of cases, though, right? Yeah. But it sounds familiar. So this is a case where there was... I feel like I want to draw a picture. It's the river. And there was a pier. And there was this barge tied to the pier. And on this barge was a whole lot of grain. This was 44. This is 1944. So this was actually grain used for the war effort. For the World War II effort. This was grain used to fight Nazis. This is important grain. But the thing is, there was... And this grain, too, was owned by the U.S. government. That's why the U.S. government's involved in the title. The thing is, though, this is a very narrow river. Let's make it a little wider. There was a lot of other barges, too, parked along this pier. And they were all kind of tied together. And I think there was... and so the Carroll Towing Company was told they have to move one of these barges. So they untied it and they moved one of the barges. And it was technically, the barges looked kind of different pier, but all of them were tied together. And there was like a pier over here and a pier over here. I can't remember the exact details. But the point is, in the process of Carroll Towing, moving the barge they're supposed to move, they unmoored or they detached all these barges as well. And this what resulted was apparently this huge mess that ultimately resulted in this barge, with all this grain on it, slamming into another barge and sinking. And the U.S. government was like, wait, what? Our grain is gone, and they sued Carroll Towing. You screwed this up. And the judge on the case was Learned Hand. And in order to, and people were talking back and forth, the sides were like, well, no, we shouldn't be liable because these things they just happen, we just have to deal with them. It's like, no, you should have been taking care, you're negligent. He sort of organized his thoughts, he sort of organized his understanding this case like so. He's like, let me actually read the quote.
Since there are occasions when every vessel will break from her moorings, and since if she does, she becomes a menace to those around her, the owner's duty, as in other similar situations, is to provide against resulting injuries as a function of three variables.
1, the probability that she will break away, which we're going to say the probability of accident. 2,
The gravity of the resulting injury if she does.
which we will call L for loss or the cost of accident. Note these things combined, it's expected value. So here's expected cost because it's a loss.
3, the burden of the adequate precautions.
So we will call it V.
burden, let's just say cost to prevent accident.
Possibly it serves to bring this notion into relief of state in algebraic terms. If the probability we call P, the injury L, and the burden B, liability depends on whether B is less than L multiplied by P,
or that. That's the learned hand rule. If the burden is less than the expected cost, so just to say if there is there's negligence. Steel-toe boots cost $200. They're dropping stuff on your feet, pretty common. Not necessarily a huge issue, but this is pretty common. We could even say maybe, there's a likelihood of like maybe a 10% chance of people dropping things on their feet every day? Or conservatively. Would you say that, we have to do some math, fancy math. How long do steel-toe boots last? Let's say they're $200 steel-toe boots on average. Give me an estimate. They last like what? About a year. Excellent. So that ends up being what? Like if we take 300. I mean, you're not wearing them literally every day. You're probably maybe working them like maybe 200 days out of the year. Just give me a number that's easy to work with. And they cost $200. That's $1 a day. Every day there's a 10% chance of dropping things on your feet. So, how painful is it to drop something heavy on your feet? How painful is it? Yeah. 7? Right, it's pretty hard. Right, are people ever out of commission for dropping something on their feet? You know, they have to be like not working for a bit. Well, yeah, but again, if you actually hurt yourself, right, you were wearing steel-toe boots, you could be out for a while, right? So we can easily say that the cost of the person, when you include the cost of pain, when you include the cost that you can't work, could be easily in the hundreds of dollars, right? Why do we say it's, I don't know, $300? Just to throw a number out. There's a 1% chance it happens. It's a cost of $3 if it does. 0.01 times 3 is greater than $1 to just buy the damn boot. I'm sorry, cost is 300. There we go. Because if you take 1% times $300, reflect that pain, that's $3. 3 is greater than $1. And I have to do it this way because it steel-toe boots cost $3, but again, you get that protection every day. So this is the daily probability. You can argue that it is required or it could be held negligent by not enforcing this very efficient rule. And this, by the way, this idea of learned hand rule comes from a branch of economics called law economics, which argues that the law is structured in such a way as to encourage economic efficiency. This is efficient because this expected loss is greater than we could just prevent the bad things from happening in the first place. This would be more efficient if we did it, so we want to punish people who don't do it. Any questions? Oh, there was only one. They had to pay taxes in the US government. Stating that there is no general rule which would give liability on bars and no under experience in court this rule. And the court ruled that leaving bars unintended. Oh yeah, so this is what, so in order for this case, they noted that there was no bargee that was around. Bargee is someone who like watches the barges and makes sure that they're fine. And like he wouldn't, such a bargee wouldn't notice that things would be coming on board and yeah, could have prevented it happening. But no one put him there.
And it's not like they're super expensive people to hire. The probability is pretty high. These things happen all the time. There's some pretty valuable stuff on these barges. I mean, it's not like a 20% chance, but it's still pretty big. And when you consider like how valuable the cargo is, how likely it is, and how much it would cost us to hire someone to be there, there was negligence. It's not like there was lightning strikes involved, right? This was a totally foreseeable problem. The court ruled that leaving a barge unattended during the daylight hours posed significant risks, such that it would be fair to require a crew member to board the ship, thus the accused was found liable for negligence for being absent from the ship without excuse, etc., etc., etc. Any questions? There's another case too. There's a few of them. There was one with someone who worked at a rail yard. And when he went one day without telling anyone who was going to be there, it was his day off. He was like, I want to catch up on some work. And his job involved like maintaining the trains. And one day he was working under a train, and he was there, but he wasn't supposed to be, so I didn't know he was there. He was working on a train, and the train moved, and it rolled over his legs, and he lost his legs, and he sued. And it boiled down to the learner handle. So it was Judge Posner. Judge Posner was on it, and you could tell Judge Posner kind of sympathized with the rail company. This is the guy who showed up, didn't tell anyone who was there, and just went about his business. And he was like, he had good lawyers. His lawyers were like, look, they could have checked underneath the rails before they checked underneath the cars before they moved them, and that would have prevented the accident. They could have blown the whistle every time a train moves. That could have prevented the accident because it would have alerted me. I could have gotten out of the way. Right? Yes, the probability is small, but the costs are huge, and these are easy things they could have done. And the defense, and you can, if you ever read Judge Posner's opinion on this, he's saying, the defense didn't give me any idea as to how expensive it would be for them to constantly have whistles blown every time a train is moved. I don't know how often trains are moved in train yards. If they're moved literally every couple of minutes, then constantly blowing whistles won't do anything. Right? It would be a cacophony of noise. At the very least, it would be so tremendously distracting, it would be hard to communicate. You know, I don't know how often trains move. Having someone run all the length of a train and then all the way back every freaking time you have something move would be incredibly expensive. But I don't know how often they move. And they didn't say so. So he had ruled in favor of the person who got his legs crushed. And you get the impression when you read the opinion, someone on the legal team was fired on the other side. It's like, you didn't do this, you didn't do this, you didn't do this, you could have done these things, you could have explained why B was really high, but you didn't do that, so I gotta assume it's really low. And there was another case involving a woman who goes out of a store at a department store. And there's a step down to leave the store. There's a sign that says caution, step down. But on this particular day, there was a lot of light. It was a cloudless day. And at this particular time, she left the store. The sunlight on this cloudless day reflected off of a building, a glass building, and blinded her temporarily so that she did not see the sign. And when she walked out of the store, she stumbled and she fell and hurt her. I think it was an ankle. And she sued, though. I think it was Winn-Dixie. I think this was the case involving Winn-Dixie. I can't remember the woman's name, though. Now, what it is, she argued that, you know, they could have had like an awning out, you know, some like protection to prevent like the light from coming in, and I wouldn't have been blinded. I would have seen the sign, I would have seen the step, it would have been fine. What do you think the judge ruled? She's crazy. Like, yeah.
Like this is like, for one, this is like super rare because it requires this like list of things that have to happen. Remember when we talked about probability and this, and it has to be a cloudless day, and it has to hit the light right, and you have to not be familiar enough with the store to know that there's a stair there already. You need the sign there, and like you have to be the right height so it would affect you, right? I wouldn't be affected because I'm taller than her, so and so the probability is shockingly low. Who freaking cares if it happens because you just hurt yourself slightly? And as they bring out, like, look, putting on an awning not only has a huge upfront cost, it also has a maintenance cost. It also can, it can block the light, so it could make the building, make the interior seem darker, and that might affect sales. It might be a problem for people walking by because it's interfering there. It's not even sure that they're allowed to put something out there because it would be out into the sidewalk, public. There was all these additional costs, and then like the judge is like, you're being totally unreasonable, lady. Okay. Any questions?
If you argue for a handrail, that is still a high cost.
You can still argue about it in cheaper. I think they come up with a lot of different things that people have done. I remember the awning part though. And I think the handrails aren't as high cost, but then you can argue that they didn't see it. We're not really glad it's being able to stay there. That's tricky. But again, like,
Probability is so low.
and it's like not, it's one stair. It's one stair, so it's not like she's falling down 85 stairs to break her back.
It's one stair. Like, so I can't imagine even a handrail would pass the test.
But I don't know, this is what lawyers would do in this case. They would try to argue that the burden is really high. Any questions? Any other questions?
Can't you with this rule? Can you like, so it seems like being a lot of examples, like they could have easily flipped it backwards and used the rule like in the complete opposite way. You know, like the cost of the lady looking, to make sure look at the ground, or like the probability of the accident is, 50-50 maybe of tripping. The burden is really they just switch it back and forth and move stuff to this.
What I would do then, if you were making that argument for the defense, I would say this is literally the only time this has happened. Like, we could say, look, we could point to medical records in the area saying, look, we haven't had like any emergency vehicles come by because other people have tripped. Because we could bring in witnesses that come in all the time saying, look, we don't have any problems with people tripping. So if you want to claim it's 50-50, I would bring in evidence that says it's not 50-50, it's just like this random event that happened. This is literally the only time this is brought forward. And then I might bring in some medical experts too. That gives me stuff about the bone and how, like, look, you can't hurt yourself that much if you fall one step. So by biology, L has to be small. Right? But this gives you the framework as to how you might work it. If you go on, and again, I should mention I'm not a lawyer, I just know this rule because one of my fields in economics is law and economics. So I think it's a really cool, interesting application of it.
But if you want to start a business, I would suggest you consult a lawyer if you want to think about this rule.
Cover my butt, etc., etc. All right. Speaking of concerns you might have if you start a business, let's move on to Bayes' theorem. So, imagine that there is a company that handles credit card information, and the person who runs that company is really concerned that some of her employees might be on drugs. Because the thinking is, she argues, if you're on drugs, you're going to be more desperate, maybe on average, maybe you need a fix, you don't have enough money to pay for drugs can get expensive, especially if you get addicted to them, you need a stronger and stronger dose to get that same high because your body built the resistance up. And since they have access to all this sensitive financial information, I'm concerned that if they take drugs, they might be tempted to steal some identity theft. Right? They might be doing some identity theft to get some money to pay for drugs. So we're going to do some drug testing. And let's imagine
after we do this drug testing, let's imagine all of your employees at this hypothetical credit card company. And it turns out Jeanette, he just came back positive for drugs. Now, sorry, Should I fire you? Why not? They came back positive for drugs.
Well, let me highlight this even more. Let's imagine that I know there is a 1% chance an employee is on drugs. I just know this maybe from some sort of larger record that we have, some larger study, that in general, drug use is maybe around 1% of the population, or 1% of my employees are on drugs. It's the kind of people who are into this business. 1% chance. So, before I did any testing, I would assume a 1% chance for all of you. Because I don't know, that's why I'm doing testing. But then it turns out, Jeanette, that's positive. Everyone else that's a negative, you're positive. So, what should I conclude? Should I fire her? Out of an abundance of caution. Anyone? Anisha? You give me this look. Like,
so you did a drug test for your company and only one person got positive?
mm-hmm.
So you want to know if you want to fire or not?
Yep. What? But she's on drugs. No, I can't. What if this is an Equifax scenario? Can you steal all the data and all this stuff?
No, you should help for instead of going through the stress of hiring and finding
I don't know. Better than living with the stress of some of my steal information. Look at her. Look at her. You got that look in your eyes. You're wearing that color. Let me ask, yeah.
But your concern is the fact that, stealing information, not the drugs. So you are correlating drugs with stealing information. Yet there is the proof that because she's on drugs, she's the one stealing information.
Sure. Sure, absolutely. So you're right to point out that just because someone's on drugs doesn't mean they're going to steal information. I'd only argue that she's a greater risk. And out of an abundance of caution, I have to let her go. But there's another thing you're skipping over, is that if she tests positive for drugs, is there a 100% chance she's on drugs? No. No. What's that chance then? If she tests positive, is it more than a 1% chance? Should I upgrade my expectations? Sure, you failed the drug test, or you passed the drug test, let's just say you got negative results, you got a positive result. But the question is, should I now say that there's a 10% chance she's on drugs, or 50% chance, or 90% chance, or 2% chance? This is this question, how do you upgrade your expectations when you get new information? How do you update them?
And this is what we call Bayes' theorem. This is the idea we're going to call Bayes' theorem.
To understand Bayes' theorem, I'm not going to give you the equation today. I'm going to do that next time. I want to give you a lot of the logic first. And the idea is the logic will be so well structured, you'll be able to get the equation really well. Okay. We're going to need a couple of things. First, we need two terms, sensitivity and specificity. Take some practice to say specificity. 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 It's tricky. Sensitivity is the ability to detect a positive state. And specificity is the ability to detect a negative state. Both are always done in terms of percent. 90% specific, 95% sensitive, 98% specific, and so forth. For example,
I think I used 80%, right?
I believe I use 80%. 80% sensitive means if 10 drug users were tested, eight would be identified as users. It would correctly identify 8 of the 10. That's 80% sensitive. Note that we're starting with assume that they are drug users. Starting with the fact that they're drug users, we will identify 8 out of 10. We identify 80% of them. %90 specific means if 10 non-users were tested. Nine would be identified as non-users. Ten non-users walk in, we give them the test, we ID 9 of them as non-users, and the other one is a false positive. Just like here, 10 drug users walk in, we identify 8 of them as users, and 2 of them are false negatives. Comes back negative, but it was incorrect. To help master this distinction, let's imagine that I wanted to have a party. It's going to be a really amazing party. There's going to be really great food. There's going to be gift bags. It's going to be really fun. But I don't want to have just anyone at my party. I only want to have certain people, because that changes the nature of the conversation. Right? If I have just anyone walk in and it's going to be conversations about basketball teams and sports, and I don't want to have that at my party. I only want to have nerds at my party. I want the conversation to be about Star Trek and the latest, like, there's Avengers movie, Infinity Wars comes out soon. Like, that's what I want the conversations to be about. So, but everyone wants to be at my party. It's going to be lots of fun. So at the door, I have to come up with a test. I have to come up with a way to sort out the nerds from the non-nerds. So let's imagine my test is, to anyone who comes in, who is Luke Skywalker's father? Thank you, answer. How many of you knew that? Surprisingly few of you knew that, but most of you did. How many of you knew that even though you were not a nerd? Many of you, right? Many of you knew that. This was a much better example last class, but a fair number of you know that even though you're not a nerd. Usually it's like almost all of them. Usually everyone knows it. You consider yourself a nerd, Michael? You do it. Yeah. Oh, okay. Well, then you're a bad example of this. There's a lot more nerds in this section than I'm used to. So, how's the sensitivity go? How many of you got it right? How many of you are nerds but did not know that? How many of you are nerds but did know that? Sensitivity is 100%, right? Every single nerd is going to know the answer to that question, right? They're not even considered to be people if they didn't know that. I'm kidding. No, but every nerd's going to know that, right? Like if you didn't know that, then you lose your nerd back. So it's no doubt. What's the specificity?
Very low.
like, how many of you, let's see, so I think maybe about half the class knew it, so that's maybe about 10 people roughly. I think that we had maybe about 4 people who knew that even though they weren't nerds. So what's the specificity? I think we had 10 people who knew that, right? So that means I think it was 10 people who didn't know it, right? So well, 10 people didn't know it, and they weren't nerds. So that's pretty good. And then there were like, I think we had about 2/3, right? So if I'm saying like, okay, how many of you knew the answer? How many of you did not know the answer to the question? Raise your hand. How many of you did not know the answer? 1, 2, 3, 4, 5. Oh, we only have 5 people who didn't know it. Okay. How many of you are not nerds? Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. Maybe about.
Yeah.
Well, this is going to be. So this is going to be. Well, it's self-description. It's self-description on how you consider yourself to be a nerd or not. So we might have like. Let's see. I think we had. I think it was maybe about 10 people were non-nerds. Let's make the math easy. And how many of you didn't know that? I think it was 4. Well, I think there were 4 people. So what's our specificity? 40%, right? Note it's 40%. Because you don't want to know it, right? You didn't know it, I correctly identified you as a nerd. But there are 6 people who are not nerds, but were able to sneak into my party. Right? So in other words, while this has 100% sensitivity, its specificity is 40%. Its specificity is really low. It's not that great. And quite frankly, that's honestly pretty good. Last time I had it, I think there were like 20 people who didn't consider themselves nerds, but 19 of them still knew the answer. So that means only one of them didn't know the answer. At first, and felt very embarrassed. It was a 5% specificity. We kind of never appreciate it. Yeah.
Then let's come back to like with this. I'm like trying. I just can't remember exactly. But doesn't this like correlate to? Doesn't science would directly correlate to the
Yeah, absolutely. Yeah, I think that's something we're gonna dive into later. But there is a sort of a type 1, type 2. It depends on what your null hypothesis is. But yeah, there's a lot of overlap between these ideas. Absolutely. How would I? So here, I gave you an example of high sensitivity, low specificity. What would be the opposite? What would be a question that would be the opposite? Michael, you claim to be a nerd.
In the episode of Star Trek The Next Generation, Moriarty, I'm not done yet. Hologram of Moriarty tries to get himself beamed off the holodeck into the real world. What alteration did the transporter make to do that? How did they try to change the transporter so they could beam a hologram off the holodeck into the real world? Come on, let's do that episode. So honestly, no, do not ask that. You don't know the answer?
I do. They decoupled the Heisenberg compensators. Duh. Yeah. So, what do you think the sensitivity of this test is?
It's like 50% every single person.
Well, I mean, no one else knew either. I asked a bunch of other people. You guys all claim to be nerds.
Like 10%.
Yeah, 10% is probably pretty high. Like, I picked it because I knew it. But I purposely structured this is such an obscure piece of information, especially since, like, it used to be that maybe there was only, like, 2 nerdy shows out, like, 2 nerdy stuff out, like, you know, Star Trek and Star Wars. Maybe that would have been higher.
But nowadays, there's so much nerd stuff out that it's likely that any person doesn't know that random bit of Star Trek trivia, especially since this was a TNG from like the 90s. So it's becoming more and more obscure. This is really low. This is probably 1 or 0.1%. This is shockingly low. But what's the specificity? Yeah, I can't. 95 seems way too low. Like, can you imagine a non-nerd knowing, oh yeah, I remember my brother was watching that while I was like making out with my boyfriend, and I think it was like a couple of Heisenberg compensators or something like that. Can you imagine the scenario that would be the case? Like, how would any person know that information if they didn't even watch Star Trek as a general thing? This is close to like 100%. Maybe you never know, 99.9%, really high. Yeah, like.
So specificity is like you're finding out the test ability to find out who doesn't know the answer.
Mm-hmm. Yeah. Who's going to be put in the no? Who's going to be the negative state? Right.
So we can ask you too.
No. The probability of the test being correct depends not only on the sensitivity or specificity, it also depends on what the test is examining. If the test is examining a nerd versus a non-nerd, or someone who is a drug user versus someone who's not a drug user, the probability that the test is right changes. So what we're going to do to keep all of this straight, we're going to go back to my drug use problem. I'm going to make a tree diagram. But this is going to be a little different than the tree diagrams before. Before the second R, I'm going to send this out, was identical. This section was identical to this section. But now we're going to note that that will change. I should probably make it symmetric, just to make it like symmetric size. Give another. So here, the person is a user and not user. Here has a probability of 0.01, which means the probability right here is what? 0.99. One way to think of these is they are conditionals. If something happens, what is the probability of this other thing? So we're going to have test is right. Test is wrong. Test is right. Test is wrong. Now, again, though I did the same labeling, the probabilities will not be the same. If someone is a user, someone is a drug user, what is the likelihood the test will correctly identify them as a drug user? 80%. Why? Exactly. So I planned this out ahead of time. Okay. Assuming someone is a positive state, assuming they are drug users, assuming this is true, 80% chance of identifying. Which means, what is the probability the test is wrong? 0.2. Not user, what is the probability? And I should also note that a right test here means the result is positive for drug use. And a test wrong here means the result is negative. Because you missed the person. What is the likelihood the test is right here? This area. So the likelihood the test is correct if you're working with not a user. 0.9. And what is the likelihood that the test is wrong? 0.1, right? We missed them. Note here, a right test is what? Is it a negative result or a positive result? Negative result, yes. Why is it negative result?
Because you're not a user, so it should be negative for drugs.
Oh, it was right. Which
which means this one is
Positive.
positive. Are we good so far? We might call this a true positive. True because it's the correct result, positive because it's a positive result. This one is what? False negative. Because it's a negative result, right? But it's incorrect. Some of you who are drug users got lucky and the test didn't detect you. I'm not looking at anyone in particular. Which one's this one? True negative. And finally, false positive. Safe to say these are the only 4 things that can happen. These are the only 4 things that can happen.
So, okay. What is the chance
Of a true positive. Yes. You will multiply what by what?
The 0.01 by 0.8.
Mm-hmm. Absolutely. Because in order for us to have a true positive, 2 things have to happen. This has to happen, and this has to happen. If you just look at 0.8 and you add all these things together to get all the possible results, you get 200%. Right? This has to happen, and this has to happen. P equals 0.008. Multiply those 2 things together. What is the chance of false negative? P equals 0.002. Note when you add these 2 things together, you get this 0.01. True negative, what's the chance of a true negative? That's right, 0.891. And finally, false positive. Are we good so far? Does everyone see where we got that from? We just took the probability of the event, and then assuming that event happens, what's the probability of this other thing? What we call a conditional. Let's get rid of this. Yeah. Oh, sure.
Can you explain why you're saying this true positive and false negative?
So, okay, let's take this one. Thank you. The test is correct, right? That's what we established. This is a correct result because we the person is a user. We identified them as a, and this is the chance that we'll identify them as a user. So that means the result is positive. We correctly identified them as a user. Hence, true positive. Here, the test came back wrong. We missed some. They are a drug user, but the test didn't catch them. So this result is negative. It is the incorrect result. The test is wrong. False negative. This result is right. Right? The person's not a user. The result is right. The test comes back negative. That's what we would expect, right? For someone who's not a user, that's a true negative. And this result is positive, but that was an incorrect result. We're thinking that they're users, but they're not. False positive. So we're good on that? Are these results mutually exclusive? Can it be false positive and true negative at the same time? No, it can only be one of these things. So to answer my original question, and we're almost there in the little bit of time we have left, what is the chance of a positive result? What is the chance of a positive result?
0.107, thank you. How'd you get that? We have two ways to get a positive result. This can happen, a true positive, or this can happen, a false positive. There are two positive results. Those two. Everyone good with me so far? Remember what we're trying to ask ourselves. Without knowing anything, there's a 1% chance of employees on drugs. And then Jeanette comes back positive for drugs. What is the likelihood she is on drugs? No. But does this seem like a good test? 80% sensitive, 90% specific. That seems like, it's not an amazing test, but it seems like a pretty solid test. Well, to answer my question, let's imagine that I tested 1,000 people. How many positive results would I have? How many positive results would I have if I tested 1,000 people? No. How many, I'm sorry, how many, no? What's the chance of a positive result? No. 107. I would have 107 positive results if 1,000 tested. I would have 107 positive results. How many results would be true positives? 8. 8. If I picked one of those results at random, one of these 107 at random, what is the chance I would get a true positive? Chance of true positive assuming positive result equals 8 divided by 107, or about you got that right, 7.48%.
0.748.
In other words, you can take the chance of a positive result no, that's fine. And do this. Or 7.48%. Because what I did here is exactly what I did right here. I just, didn't multiply by 1,000. In other words, Jeanette, it came back positive. But even though it came back positive, well, this test seems like it's pretty good. It's not. I go from a 1% chance of thinking that you're on drugs to now about a 7.5% chance that you're on drugs. That's not huge by any measure of the word. This seemingly good test is actually not that good at all. I mean, granted, I updated it, I went from 1 to 7. But it's still really low. I'm not sure you're going to be fired over that. This is something to keep in mind. And the reason, does anyone know, does anyone know why it's so low? Why it's not something closer to 50 or 80%?
Well, it seems like it's because there's such a high probability of people not using drugs that probability is multiplied across the board.
Mm-hmm.
That's just what causes it so high.
Yeah, exactly. This is what this part is right here. Right, the reason why this is so low is because the false positives overwhelm the true positives. Look at this. The false positives are about more than 10 times as large, more than 10 times as likely, more than 12 times as likely as the true positives. And so when you are testing for something rare, like drug use, or terrorists, or a rare disease, or a rare condition, That means by definition, there's a lot of non-states out there, a lot of no's out there, a lot of non-users out there. And even if the test is seemingly good, the false positives can overwhelm the true positives. And you don't learn that much.
Any questions? So, in general, Bayes' rules teaches us two things. One, it teaches us how to update our expectations when we get new information. I went from a 1% to a 7.5%, 7.48%. And two, a subtle lesson there as well is that when you're testing for something rare, it's really hard to understand what's going on. Because by definition, rare things will also have a lot of false positives. And you need a really, really, really high specificity to overcome the rare event. Right. We'll talk more about this next class. Well, then I'll give you the formal equation for Bayes' theorem, and we'll show you how to do set up an Excel so maybe build your intuition before. See you then. Have a great time.